Let's look at the concept of independent events in probability. Here, I'll discuss the formal definition of independence of two events, work through some problems, and try to help you visualize the concept in different ways. I assume you're already familiar with conditional probability. Let's start with the formal definition of independence, and then try to fully understand the meaning. Events A and B are independent if and only if the probability of their intersection is equal to the product of their individual probabilities. Well, at face value, that's simple enough. We can use this identity to find the probability of the intersection from the individual probabilities if we happen to know that A and B are independent. We can also use this identity as a check for independence if we know the probability of the intersection and the individual probabilities. While this is the formal definition of independence, most find it easier to understand the meaning if it is thought of in terms of conditional probability. So let's have a look at that. Here are the conditional probability formulas for the probability of A given B and B given A. Note that the conditional probability is only defined if the probability of the event we wish to condition on is not zero. When A and B are independent, the probability of the intersection turns into the product of the individual probabilities, like so. And when we cancel terms here and cancel terms here, we see that under independence, the probability of A given B equals the probability of A, and the probability of B given A equals the probability of B. Let's bring all those together. When events A and B have non-zero probabilities of occurring, the following three statements are equivalent. The probability of the intersection equaling the product of the individual probabilities, the probability of event A given B equaling the probability of event A, and the other way around, the probability of B given A equaling the probability of B. Each of these statements implies the others. If one is true, they are all true, and A and B are independent. If one is false, then they are all false, and A and B are not independent. Some people use one of these as the definition of independence, but if we do that, we run into a couple of snags. First, we have this awkward bit of the ordering of A and B, and unless we write it in both ways, we need to explain why we only need one of them. Second, the conditional probability is not defined if the event we condition on has a zero probability of occurring. So I think we're best off if we stick with the first one as the definition of independence. But the meaning of independence is easier to understand if we think of it in terms of the conditional probabilities. Here, the knowledge that B occurs does not change the probability of A. Suppose the events are independent and I have a bet on event A. If I'm told that event B has occurred, I am indifferent to that information. The probability of A has not changed, so neither has my chance of winning the bet. When events are not independent, then the knowledge that one event has occurred changes the probability of the other. If the events are not independent and I had a bet on event A, then the knowledge that B has occurred will change the probability of event A. This will either be good news for me, the probability of A has gone up, or bad news, the probability of A has gone down. This is important, so let's look at that one more time in words. When two events are independent, the occurrence of one event does not change the probability of the other event. Now let's look at a few examples. Suppose the probability of A is 0.7, the probability of B is 0.2, and A and B are independent. What is the probability of their intersection? Well, this is a very simple question. Since we know that A and B are independent, the probability of their intersection is simply the product of their individual probabilities. Here, that's 0.14. If we hadn't been told A and B are independent, then we couldn't find the probability of the intersection. There is no way of finding the probability of the intersection from the individual probabilities alone. So independence can at times make our lives easier, as it makes finding the probability of the intersection easier. Note that here, since A and B are independent, the probability of A given B equals 0.7, just the probability of A, and the probability of B given A is 0.2, just the probability of B. We could verify this easily with the conditional probability formula. Now suppose the probability of A is 0.4, the probability of B is 0.8, and the probability of their intersection is 0.36. Are A and B independent? Since we are given the probability of the intersection, Independence is easiest to check by checking whether the probability of the intersection is equal to the product of the individual probabilities. Here, the product of the individual probabilities is 0.4 times 0.8, or 0.32. This is not equal to the probability of the intersection, which is given as 0.36, so A and B are not independent. The probability of the intersection is greater than it would be under independence, so A and B have a greater probability of both occurring together than would be the case under independence. We've answered the question as posed, but if we were to calculate the conditional probabilities here, we'd find that the probability of A given B is 0.45. So the knowledge that B has occurred has increased the probability of A. The probability of B given A is 0.9, and so the knowledge that A has occurred has increased the probability of B. Note that these conditional probabilities are both greater than the unconditional probabilities. When A and B are not independent, then these conditional probabilities will either both be greater than the unconditional probabilities or both be less than the unconditional probabilities. Let's look at another example. Suppose a balanced six-sided die is about to be rolled, and we define the following events. A occurs if a 1 or a 2 comes up on the up face of the die, and B occurs if the number is a 2, 3, 4, 5, or 6. Do these two events look independent to you? Let's see. Here a natural definition of the sample space is the set of the 6 possible outcomes, the numbers 1, 2, 3, 4, 5, and 6. And if it's a balanced die and we're rolling it fairly, then it's reasonable to assume that the 6 possibilities are equally likely. So the probability of A is 2 over 6 or a third, and the probability of B is 5 over 6. Here A and B intersect at the number 2, so the probability of their intersection is 1 over 6. The product of the individual probabilities is 5 over 18, which is not equal to the probability of the intersection, 1 over 6 or 3 over 18. So A and B are not independent. If we thought of this in terms of conditional probabilities, the probability of A given B is 1 over 5, as only one of the 5 equally likely numbers in B is also in A. This is much less than the unconditional probability of A of 1/3. The knowledge that B has occurred eliminates the number 1 as a possibility, and that really bashes down the probability of A in this case. A and B occur together less often than they would if they were independent events. And the probability of B given A is 1/2, as only one of the 2 equally likely numbers in A is also in B. So the conditional probability of B given A is less than the unconditional probability of B. Let's try rolling a die again with the same event A, but with this event C. C occurs if an even number comes up. Do you think these two events are independent? Well, they are. Knowing the value is an even number doesn't change the probability that it's a 1 or a 2, and vice versa. But let's see how we'd show that formally. The probability of A is still 1/3, of course, and the probability of C is 3 over 6 or a half. Let's work with just the conditional probabilities this time, as I have another point that I'd like to make. What is the probability of A given C? If we know that C has occurred, then our sample space is reduced down to just C, just the even numbers. Only one of the 3 equally likely sample points in C also occurs in A, the number 2. So the probability of A given C is 1/3. That equals the unconditional probability of A, so A and C are independent events. Knowing the die came up even does not change the probability the die came up with a 1 or a 2. I do have another point I'd like to make, so humor me for a moment. C complement is made up of all the sample points in the sample space that are not in C, so C complement is the odd numbers, 1, 3, and 5. What is the probability of A given C complement? C complement is made up of 3 equally likely values, and one of those, the number 1, is also in A, so the probability of A given C complement is 1/3. Wait a minute. The probability of A given C complement is also equal to the probability of A, so A and C complement are independent events as well. Knowing the die came up odd doesn't change the probability it's a 1 or a 2, and vice versa. And that leads to the following discussion. If events A and B are independent, then so are the following pairs of events. A and B complement. There's a simple argument for this. If knowing that A has occurred doesn't change the probability of B, then it doesn't change the probability of B complement, as that's simply 1 minus the probability of B. So it stands to reason that if A and B are independent, so are A and B complement. This isn't very difficult to prove mathematically, but I'll leave that for another day. And we could, of course, switch the roles of A and B in that argument. And if we use the same hand-waving argument an additional time, we also end up with this. If two events are independent, so are their complements. If A and B are independent, then knowing that A occurs doesn't change the probability of B. And knowing that A doesn't occur doesn't change the probability that B doesn't occur. That knowledge might help us understand independence a little more deeply, help us with some probability calculations at times, and help us visualize problems in different ways. Let's look at an illustration of that. Suppose we have this scenario, where the probability of A is 0.6, the probability of B is 0.7, and the probability of the intersection of A and B is 0.42. So A and B are independent here, since the probability of the intersection is equal to the product of the individual probabilities. Now let's draw a bar plot where the heights of the bars represent the probabilities of A and A complement, which, in this situation, are 0.6 and 0.4. Now I'm going to divide those bars, illustrating the probabilities associated with B and B complement along with A and A complement. Here, event B is represented by the blue portion of each bar, and B complement by the red. So in this A bar, the height of this blue portion represents the probability of the intersection of A and B, and the height of the red portion represents the probability of the intersection of A and B complement. Stacked on top of one another, they make up the entire probability of A. And we'd have the corresponding interpretation of the red and blue colors within the A complement bar. When A and B are independent, as they are here, the proportions of red and blue are the same in the two bars. The blue portion, corresponding to event B, makes up 70% of the A bar, the bar on the left, and 70% of the A complement bar, the bar on the right. Whether we are within A or within A complement, the red-blue ratio is the same. The probability of B is 0.7, whether we know A has occurred, we know A complement has occurred, or we know nothing at all. But what if A and B are not independent? Suppose we have this situation, where the probabilities of A and B are the same as what we just had, but the probability of the intersection of A and B is 0.55, much greater than it was under independence. Then much more of the A bar on the left is blue, corresponding to the probability of the intersection of A and B, and much less of the A complement bar is blue. Here, the knowledge that A has occurred makes it much more likely that B has occurred. The knowledge that A complement occurred makes it much less likely that B has occurred. Overall, B still has a probability of 0.7 here, but more of that occurs with A, and correspondingly less with A complement, than was the case under independence. Let's change this 0.55 to 0.32 and see what happens. Here, the probability of the intersection of A and B is 0.32, much less than the probability of the intersection under independence. This means that A and B are less likely to occur together than they are under independence, and we get much less blue and much more red in the A bar on the left, and correspondingly much more blue and much less red in the A complement bar. Overall, B still has a probability of 0.7 here, but less of that occurs with A and more with A complement than is the case under independence. With this in mind, let's look at a simple example involving playing cards. Suppose we are about to draw a card from a well-shuffled 52-card deck of playing cards. Here are the 52 sample points, the ranks ace through king for each of the 4 suits. If the deck is well shuffled and the card is being drawn fairly, then it's reasonable to consider these 52 sample points equally likely. And consider the events the card is an 8 and the card is a face card. Are these events independent? In case you don't know, the face cards are the jacks, queens, and kings, the three right columns in the table of cards. What do you think? I'm pretty sure these events are not independent. Knowing the card is a face card completely eliminates the probability it's an 8, so the probability of an 8 would change under the information that the card is a face card, and that means that drawing an 8 is not independent of drawing a face card. Let's see how we'd show that formally. Let's go with the conditional probability route again and see if the conditional probability of drawing an 8, given the card is a face card, equals the unconditional probability of drawing an 8. It would be just as easy to condition on drawing an 8 instead, but let's go with this one. For the unconditional probability of drawing an 8, since the 52 sample points are equally likely here, the probability of drawing an 8 is just the number of 8s over the total number of cards, 4 out of 52 or 1 out of 13. Now for the conditional probability. What is the probability the card is an 8 given it is a face card? The information that the card is a face card reduces the sample space down to just the face cards, just these 12 equally likely cards. The probability the card is an 8 given the card is one of these 12 is, well, 0 over 12, or 0. There are no 8s in that reduced sample space. So the probability the card is an 8, given it is a face card, differs from the unconditional probability the card is an 8, and that means that these two events are not independent. The information that one occurs changes the probability of the other. Another way to think of that is that the probability of drawing an 8 from among the face cards differs from the probability of drawing an 8 from among the non-face cards, and vice versa. Now suppose we have a similar situation, where event E is still the event we draw an 8, but now we have event H, representing drawing one of the hearts. Are these two events independent? They are in fact independent, as the information the card is a heart doesn't change the probability the card is an 8. The 8s are equally represented among the hearts and the non-hearts. But let's see how we'd show that formally using the same method. The probability of drawing an 8 is still 1 out of 13, of course. Now, if we condition on the card being a heart, that reduces the sample space down to just the 13 hearts, just these 13 equally likely cards. What is the probability the card is an 8 in this reduced sample space? One of the 13 equally likely hearts is an 8, so the probability the card is an 8, given it is a heart, is 1 out of 13. And this is equal to the unconditional probability of drawing an 8. And thus drawing an 8 is independent of drawing a heart. The information that the card is a heart does not change the probability that it is an 8. And that also means the information the card is an 8 would not change the probability it is a heart. These two events are independent. Knowing that one occurs does not change the probability of the other. Sometimes, due to the nature of the problem, we assume independence between events. For example, suppose we toss a fair coin twice. In most practical situations, it's reasonable to think that the outcome of the first toss yields no information about the outcome of the second toss, so it's reasonable to assume independence between these events. But keep in mind that this is an assumption. There's no way to prove mathematically that these two events are independent. That simply cannot be done. It's just a reasonable assumption based on what we know of the situation. And we do make that type of assumption frequently in probability and statistics. But in general, it is a little dangerous to simply assume independence, since if that assumption is incorrect, then our probability calculations will be wrong, and we'll get wrong, possibly very misleading results. And sometimes there can be subtle, non-obvious dependencies that we don't recognize. It's a bad idea to simply assume independence unless we have a very strong justification for that assumption. One last thing. There is a substantial difference between the meaning of the term independence in everyday English and the meaning of the term in probability, and I think that leads to confusion at times. Let's look at an example to illustrate. Suppose we have this scenario where Pete and Tom live in the same small city but don't know each other and have no real connection. Suppose we have the events A. Pete goes golfing next Saturday, and suppose for the sake of argument the overall probability of that is 0.2. Event B is the event that Tom goes fishing on that day. Suppose the overall probability of that is 0.13. Are these events independent? We might say in English, outside of a probability context, that Pete and Tom make their decisions independently. Pete and Tom have no connection. Pete doesn't care or even know what Tom does, and vice versa. But that doesn't mean these events are independent in a probability sense. Although we can't check this mathematically with the given information, in any practical scenario, these events would not be independent. Tom and Pete are both influenced by other common factors, the major one here being the weather. Both of these events are much less likely to occur if a severe thunderstorm rolls through, say. And there would be other, more subtle factors linking them together. It's hard to imagine a scenario in which they would be truly independent events in the probability sense. So the meaning of the term independent is a little different when used in a probability context than when used in everyday English. Try not to let that cause any confusion. Probability concepts can be tricky enough in their own right, and don't need any extra layers of confusion.